Okay, so thank you, Andy. It's an honour to have the opportunity to present our work today, and a real bonus to receive the prestigious Raggett Award. This morning I want to talk about our work on the electrical conductivity structure of Australia and applying that work to contribute to the study of hazard posed by geomagnetic induced currents to electrical power networks. And as Andy just explained, while I'm doing most of the talking this morning, Liejun is the primary author of the work, and he and I have worked together for many years in the GA's Geomagnetic Observatory program, and he specialised in magneto-telluric data and crustal conductivity. And at the end of this presentation he'll come up and make any clarifications and perhaps answer any questions that do arise. So nothing's done in isolation, and we have a number of people that helped us out with this work, and I'd just like to acknowledge them today. And firstly, past and present members of GA's geomagnetism team have been involved directly and indirectly in this work through the collection and processing of geomagnetic data and in the derivation of the conductivity model, which I'll be presenting later. We had a group of international collaborators too. Chai from Thailand, who developed the 3D inversion code that we used, and Ogawa-san from Japan, who made that code available to us and was very generous with his expertise, his advice and his time. I'd also like to thank Masahiro and Kiyoshi from Japan, who ran a collaborative project with GA to collect some data from Central Australia, and we'll be using that data, presenting that data a little bit later on. And finally, Dr. Shyamalan and Barton, who had the foresight and leadership to plan and execute the Australia-wide array of geomagnetic stations, the AWAGS experiment, and the data from that experiment makes up the fundamental data set which we used for this work. So just an outline. It's really a talk in three parts. Firstly, I'll just talk about the broad-scale 3D electrical conductivity model of the Australian continental crust and upper mantle, and its application in revealing geological structure. Secondly, I'd like to talk about the hazard of geomagnetically induced currents and how a knowledge of that conductivity structure is a necessary input to answer some of the questions in the study and characterisation of GICs. And thirdly, we'll show how the conductivity model can be applied in real-world data to calculate induced electric fields, which are the input for GIC studies. So the link between electricity and magnetism is well understood and described by Maxwell's equations, which say, amongst other things, that a time-varying magnetic field induces electric currents in conductive material, and electric currents flowing in conductors create magnetic fields. So the fundamental data sets for studies of Earth conductivity are a time series of variations in the geomagnetic and the geoelectric fields to measure the inducing field and the induced electric field. And so by applying some reasonable assumptions about the nature of these source fields, that sort of data can reveal information about the Earth's electrical conductivity structure. And investigations into the Australian continental conductivity have been underway for many decades really in Australia, and regional scale conductivity structures have been identified and studied, many of them by people in this room actually. So there are essentially two ways to get the required data. And on the left is a schematic of the first way. It's called the geomagnetic depth sounding, or GDS method, where time series of the magnetic flux density, the B vector, is measured in three orthogonal components, X, Y and Z. And the inducing magnetic fields assumed to be a plane wave, magnetic variations in the horizontal plane, which originate from time-varying magnetic sources from the upper atmosphere and the magnetosphere. And as the magnetic data collected on the surface of the Earth are far from the sources, the variations in the vertical component are much smaller than in the horizontal components. So these horizontal magnetic variations induce electric currents in subsurface conductors, and those currents create secondary magnetic fields which are then primarily measured by the Z component of the magnetic field. And on the right is a schematic of the magneto-telluric or MT survey, where variations in both the B vector, the magnetic vector, and the electric field, the E vector, are measured. So the time variations in the inducing magnetic field are measured with a vector magnetometer, and the induced electric field are monitored directly by measuring voltage, the voltage between 2 points connected by long wires. And typically they're 100 metres or so, those wires, and they're connected to the ground with electrodes. And often MT surveys also measure the vertical component of the magnetic field for additional data. So there are pros and cons for each of these methods. Logistically, the GDS method has the equipment is much more compact and easier to set up. The wires required to measure the electric field require a large area, and they can be easily disturbed by animals or other activity. And the electrodes can introduce some artefacts in electric field data when you measure for a long period of time. So MT data provides better depth information than the GDS data, but the GDS data are not affected by galvanic distortion, which can complicate MT data. So it's this GDS survey data, magnetic field variations, which were collected at the AWAGS stations, which we're using for our study here. So the Australia-wide array of geomagnetic stations was an experiment run in the early 1990s, and it was made up of about 55 locations where the time series of the magnetic field were recorded simultaneously and continuously for about 9 months, with the sampling rate of the magnetic field at was 1 minute. So the locations of the stations are shown here on the map, and the average spacing is about 275 kilometres. Now this AWAGS data set is now 25 years old, and it's a real testament that it continues to yield valuable insights into the magnetic and electric structure of the continent as we improve our theory and in our computing power to extract more information from the data. So at the time of the AWAGS survey, early 1990s, there were 4 permanent magnetic observatories shown in red on the map there, and they're used in the analysis we're looking at today. And since then we've had 2 more additional observatories at Alice Springs and Kakadu. And also note there's no AWAGS stations in Tasmania, so some of the maps we look at later on have a distinct lack of detail in Tasmania. So the geomagnetic depth sounding method uses an empirical relationship between the horizontal and the vertical components of the magnetic field, and in the frequency domain, variations in the vertical field can be represented as a linear combination of variations in the magnetic field of the horizontal components, the Bx and the By components. And the coefficients there, the Tx and Ty's, are called the vertical transfer functions, or VTFs. So the transfer functions for discrete frequencies in the time series have both real and imaginary parts which reflect the phase differences between the induced and the inducing fields. And the transfer functions can be displayed on maps using induction arrows by plotting the components of the Tx and the Ty, where the length of the induction arrow is the combined magnitude of the Tx and the Ty, and the directions are set by the relative magnitudes. And if you use the so-called Parkinson convention, those induction arrows point towards the location of good electrical conductors, and the length of the arrow indicates the magnitude of the electrical conductivity contrast. Now the theory of magneto-tellurics tells us that the depth of penetration into the subsurface depends on the frequency of the inducing signal and the conductivity of the subsurface. So for high frequencies, the variations respond to shallow conductivity contrasts, and for low frequency or longer period variations, responds to deeper contrasts. So you get a series of induction arrows at each point at different frequencies, like that. And in subsequent slides we'll be looking at some maps with these induction arrows at the AWAG stations. But before we get to that, I thought it was just worthwhile having a quick look at some geomagnetic time series data such as would have been collected at the AWAG stations. And this is a 24-hour, two plots of 24 hours of magnetic variations at the Liejun Magnetic Observatory and the Canberra Magnetic Observatory on a relatively disturbed magnetic day. So Liejun's located on the west coast, about halfway up in Western Australia, and the Canberra Observatory is about 20 kilometres away from us here in Cowan Forest. So I just wanted to point out the first thing is that the similarity between the horizontal components of the magnetic field, the red and the blue are the X and the Y components, the two horizontals. So at each observatory they look somewhat similar. But even in this data, which is time domain data, the green, the vertical component at the bottom between the two observatories looks really quite different. But it does share features with the horizontal components at the observatory that it was measured at. And it's interesting to see that for Liejun, the green vertical component seems to have positive correlation with the blue Y component, and at Canberra the Z component seems to have a negative correlation with the Y component. And if you consider this in the context of the locations of the two observatories, when you think that there's a strong conductivity contrast between the land and the salty water of the deep ocean to the west of Liejun, and a similar contrast to the east of Canberra, if you work out the vertical transfer functions for this data, they'll reflect that situation. And this is some data from the Alice Springs Observatory in Central Australia, which is far from any dominant conductivity contrast from the ocean, and there's a much weaker correlation between the Z components and the X and Y components. Okay. So the AWAG's data were analysed to calculate vertical transfer functions and plot the induction arrows, and we did 7 periods of data for the transfer functions. And that ranged from between 6 minutes and almost 3 hours. And I've just highlighted on the side there the 6-minute one and a 30-minute period, because we're looking at that data a little bit later on in the presentation. So there's a lot of information on this slide. First of all, it shows the real induction arrows for the seven periods at all the AWAG stations and the observatories. That's overlain on the broad-scale geological structure of the continent, and also shown as the red lines are prominent interpreted conductivity contrasts or features which have been identified over the last several decades from previous work and also from this AWAG's data set. So the thing that is very clear, the induction arrows around the coast point out to the deep ocean, and that's the well-known coast effect. And inland, the arrows are much shorter and they generally point towards those interpreted conductivity anomalies. I'll just point out too, this is the Liejun Magnetic Observatory here and the Canberra Observatory there. So those induction arrows are pointing essentially in opposite directions, as we could see in the data before. And for the Alice Springs Observatory, they're much shorter, and because there's no really dominant conductivity contrast in that area. So it was these AWAG's vertical transfer functions, both the real and the imaginary transfer functions, that were used as input to derive a 3D conductivity model of Australia. So we ran inversion on the data in conjunction with our Thai and Japanese colleagues, and the model space was made up of 21 variable thickness layers over an area shown in the blue there. It went from the surface down to about 640 kilometres, and each layer was split up into half-degree sized cells, so about 55 by 55 kilometres, and there were two larger cells on the edge just to account for some edge effects. And the inversion scheme we used, the WSINV 3D MT, used three starting models, or three initial models. A starting model which was essentially a one-dimensional layered model representing typical conductivity values. An a priori model, which is shown here in the blue, which I'll refer to as the ocean continent or OC model, which sets typical values for conductivity on the land and the ocean and incorporates ocean bathymetry into that. There's also a control model which holds some of the well-defined cells to be constant, namely that the ocean cells were unchanged in the inversion process. So we did try various a priori models, ocean, continent and some continental geology as too, such as the geological basins and so on, but we settled on that simple 3D OC model at the top there. Now, of course, there are significant simplifications and limitations in the model, and the AWAGS data meant that the cell size had to be large, so there's horizontal resolution is coarse, and the 1 minute sampling rate for the AWAGS data means that the shallow depth resolution in the data is not good, so there's probably not too much detail down to about 10 kilometres or so. So this is a summary of the model. It's an animation going through the 21 layers of the model from shallow to deep, where the red colours are areas of high conductivity and the blue are low conductivity or high resistivity areas. Now you would have noticed the first few layers were not much detail, and they just basically reflect the ocean continent a priori model. There was conductivity resolved in the middle layers, and as you get to the very deeper layers, the resolution just decreases again. So just to highlight some of the key features, the colour scale on these plots is slightly different to the ones on the previous animations. So at 25 kilometres depth, the model I think has improved the imaging of previously identified conductivity anomalies in the Canning Basin in Western Australia and in Queensland, southwest Queensland and Carpentarian areas. And it also suggests that those Queensland anomalies might persist down to about 100 kilometres. At about a depth of 52 kilometres, the model highlights the differences in conductivity between the Archean cratons in Western Australia, the resistive Yilgarn here compared to the more conductive Pilbara region. And at upper mantle depths, that's 132 kilometres, there were 5 new conductivity anomalies which were resolved for the first time with this analysis of the AWAGS data and the 3D model. So that's the model, and that brings me to the second part of the talk today. Where I'll be discussing another important application of Earth conductivity, and that's in the study of space weather and geomagnetic induction hazard. So space weather is primarily caused by activity on the sun, and it's the source of really a quite impressive range of hazards to us here on Earth, including most geomagnetic rapid variations and geomagnetic storms. And this image here depicts many of those space weather hazards, including the increase in high energy particles that strike the Earth during solar storms, the effects on the operation and the orbits of satellites, the degradation of HF radio signals and other radio signals that pass through or bounce off the ionosphere, like GPS satellite navigation signals. The one we're particularly interested here today is telluric Earth currents, which can affect long man-made conductors such as electrical electrical power network and pipelines. Because in addition to inducing currents in crustal scale conductivity anomalies, the magnetic storms also induce currents into large man-made grounded electrical infrastructure. And if those currents are unmanaged, they do have the potential to cause catastrophic damage to transformers in the network, and they also increase the rates of corrosion in pipelines and reduce the useful life of those pipelines. So there have been a number of very well documented problems that have been caused by large geomagnetic storms in the electricity infrastructure, and probably the first time it was noticed was in the 1850s in the telegraph network, and I'm sure you've all heard about the very famous March 1989 power blackouts in Canada caused by an extreme magnetic storm. There's also been other problems in power grids, mostly in high latitudes in areas like northern Europe, where GICs have caused power blackouts in the network. So magnetic activity tends to follow the 11-year solar cycle, and each cycle there's often one or maybe a handful of extreme storms. And the largest storms which cause problems are often given names, such as the Bastille Day event of 2001 or the Halloween storm of 2003. So in Australia, we have a fully connected electricity grid, and it's running north-south from Port Douglas to Hobart and east-west from Sydney to Port Lincoln, and that's shown on the left there. We also have a significant pipeline network, and that's the gas pipeline schematic there shown on the right. Now, geomagnetic activity tends to increase with latitude, and although Australia's mostly in mid-latitudes, there have been GICs measured in the Australian network with magnitudes of around 5 amps, but in high latitude areas they're known to get up to tens of amps. And as far as we know to date, there haven't been any known problems from GICs in the Australian grid, but there are documented problems in New Zealand and in South Africa, which are on similar latitudes to us. So it's important really to understand the GIC hazard, because the consequences of power problems are very significant. So the GIC hazard is controlled by two main factors. Firstly, by the nature of the inducing field. That's the magnitude and the frequency of the variations in the magnetic field, the earth conductivity and the subsequent induced electric field. And secondly, by the actual currents which are going to be flowing in the network, and that's controlled by the parameters of the network, such as its length, its orientation, the electrical properties like the resistance and the grounding points in the network. So that means the study of GICs can be quite neatly divided into two steps. The geophysical step, the first step, it attempts to understand and map the deriving surface electric field caused by the geomagnetic variations, and the engineering step takes that information and uses it together with electric circuit theory and the network parameters to calculate the resulting currents that are going to flow into the network. So here at GA, we're addressing the first step, the geophysical step, to characterise the induced electric fields. And the engineering steps being studied by others, namely Space Weather Services, the Bureau of Meteorology, and the electrical grid operators. So to address the geophysical step, we need to understand the relationship between the magnetic and the electric fields and the earth conductivity. And in the frequency domain, the electric field E, which is measured in volts per metre, is related to the magnetic field H, amps per metre, by the magneto-telluric impedance tensor, the Z matrix there, and that's measured in electrical resistance, ohms. And it's the Z matrix that contains the information about the subsurface conductivity structure. So the elements of the Z have both real and imaginary parts, reflecting the phase differences between induced and inducing fields. This is a very well-known magneto-telluric relationship, and it's usually expressed here in E as E and H. But the magnetic intensity, the magnetometers on the ground and at magnetic observatories generally don't measure H, they measure B, the magnetic induction or magnetic flux density, which is related to H by the magnetic permeability. So for our application, we're going to recast the equation into terms of the electric field and the magnetic induction B. And that means that the Z matrix we refer to as the M matrix, the magneto-telluric response tensor. And the units of that are millivolts per kilometre per nanotesla. If you consider a normalised magnetic field, linearly polarised in either the X or the Y direction, north or east direction, this response tensor can be displayed using telluric vectors to show the induced electric field. And they can be displayed on maps in a similar manner to the vertical transfer functions where we were looking at the induction arrows we were looking at before. So before we look at some of those maps, I just want to quickly point out the dimensionality of the subsurface and the relationship to the magneto-telluric response tensor. So if the subsurface is a one-dimensional conductivity feature, so it's either a half space or it's just conductivity which is varying with depth only, the response tensor takes on the simplified form over there with the diagonal elements 0 and the off-diagonal elements equal and opposite. For a 2D subsurface where the conductivity is changing in 2 dimensions, depth in one horizontal direction, the off-diagonal elements are different, but the diagonals are still 0. And for a 3D subsurface, the response tensor is fully populated like we see there. So using that information, we can draw hypothetical event maps to show the electric field induced by theoretical geomagnetic variations which are polarised in either a northerly direction or an easterly direction. And the colour scales here on this map shows the magnitude of the regional electric field, which is calculated from the off-diagonal elements of the tensor. And the arrows are the telluric vectors, the real components of the telluric vectors, and we just plotted them at the locations of the AWAG stations. This is an example from a simple 2-layer, one-dimensional model, so there's no reference to conductivity contrast between land and ocean, and it's for a magnetic variation with a period of 360 seconds. So you can see the induced field is uniform across the country, with a northerly magnetic polarisation inducing electric fields in the east-west direction and easterly magnetic polarisation in the north-south direction. The magnitude of those is around 2 millivolts per kilometre per nanotesla for this 360-second magnetic variation. So I show these two plots because they set a baseline for comparison really from the images I'm going to show you later, and allow us to compare the spatial patterns of the induced electric field. And many GIC studies use simple 1D or half-space models such as this as the geophysical starting point for the engineering problem of calculating the induced currents in electrical networks. So we know the Australian conductivity picture is more complicated than a 1D layered model, and this figure shows a similar hypothetical magnetic event map for a northerly and easterly polarisation using the ocean continent a priori model which I discussed before. So this model does account for the conductivity contrast between the land and the ocean, but it doesn't include any conductivity anomalies on the land. And there's a significantly more interesting picture there, I think. So the centre of the continent looks much like the 1D response, but there are enhancements and distortions in the direction of the induced electric field caused by the ocean continent land effect around the edges of the ocean. So progressing that one step further, from the simple 3D to our full 3D conductivity model, we see a different picture again, and it shows all the features of the OC model we just looked at, and with added detail of the onshore conductivity structure. And that includes enhanced fields in areas of resistive continents, such as this here in the Yilgarn here, where in some places the electric field is double what the simpler models calculated. There are reduced electric field in the more conductive areas, such as in the southwest Queensland area. And generally there's less distortion in the electric field in central southeastern Australia, where there's smooth variations in the conductivity contrasts. So by using a full 3D model as a geophysical starting point for GIC studies, it provides far more detail and highlights the dependence of the induced electric fields on the conductive structures of the continent. This one shows the results of the full 3D model with a longer period magnetic event. This is a 30-minute magnetic variation. So the electric field here is essentially responding to conductivity deeper within the model. So these hypothetical event maps, which we're just looking at, show the relative differences in the induced electric field across the continent. But for a real magnetic storm, it's not polarised in just the northerly or the easterly directions. It can have variations of hundreds or even thousands of nanoteslas across a broad range of frequencies, and it has spatial variability, north to south and east to west. So we applied our 3D model to progress from these hypothetical maps to reality by using real geomagnetic data and to calculate the induced electric field. So this brings us to this final section of the talk. And so the magnetic field is routinely measured at magnetic observatories and elsewhere in Australia, and over many decades for some of the observatories we have. But in Australia, the electric field is not monitored routinely in an observatory type situation. It's only generally monitored for short-term field campaigns. But it's the electric field that's required as input to the engineering step of GIC studies. So we do have some relatively long-term electric field data which were collected in a collaborative project between GA and some Japanese colleagues I mentioned before between 2007 and 2010 from sites near Alice Springs, at Hamilton Downs and at Owen Springs. So the data was collected over a 4-year period, but we got about 2 years of useful data because we'd have some trouble with equipment and cables being damaged and so on. And for this survey, the electrodes were placed 1,000 metres apart, and the picture here shows the cables being installed, and shows one of the electrodes being buried into the ground there. So we have used those data to test our conductivity model in the geophysical step of GIC studies. And we've used the electric field data from Hamilton Downs and the magnetic field data from the Alice Springs Observatory. And both those data sets were recorded with a 1-second sample rate. So the hypothetical event maps we were looking at before showed electric field and telluric vectors for single specific periods. We looked at 360 and 1800 seconds. But to calculate the time series of the electric field, we need the response tensor across the full spectrum. And on the right, we've got the 4 elements of the response tensor plotted here. So there's the real and the imaginary parts to each of those. Those response tensors are calculated from observed data collected from Alice Springs and Hamilton Downs. And they're across a period of about 20 seconds to about 20 hours. And on the left, we're looking at 24 hours of magnetic data from the Alice Springs Observatory at the top. So that's the northerly and easterly variations overlaying one on the other, blue and red. and it's a relatively disturbed magnetic day in Alice Springs. We've also shown there the northerly and easterly electric field measured from the Hamilton Downs site. And you'll note there in the Y electric field we're getting magnitudes of about 100 or so millivolts per kilometre. So if we use the relationship between the E and the B fields and the response tensor, we should be able to reconstruct the electric field time series. So we tried that with the measured response tensor here, and we've overlain the reconstructed electric field in red on top of the measured electric field, and the differences between those two data sets are shown in the smaller panels, the DX and the DY. So I guess as you'd hope, it's a fairly good fit. The match is good, and there's only 1 or 2 millivolts per kilometre differences. So we then used the measured magnetic field and the response tensor from our 3D electrical model from the Alice Springs area to again derive the electric field. And the response tensor from the model is shown as the dots, the real and imaginary parts, the blue and the red. And we derived the time series electric field using those data, and again overlaying here. And not such a good fit. But you really can't expect a perfect fit here, because the short period data is not really represented in the response tensor. And the longer term trends follow the features fairly well. And the largest differences, which are up to about 40 millivolts per kilometre, are during the very rapid magnetic variations, which are really outside the model, the tensor, the frequency range of the tensor. So I hope it shows that with measured magnetic field and the conductivity model, you can derive a reasonable estimate of the local electric field, which can be applied in the engineering step to calculate GICs in networks and induction and for hazard and risk modelling. So I've demonstrated the application of the geomagnetic and electric fields for Earth conductivity modelling, and how the 3D model can be used to improve our knowledge of the structure of the continent, and it can also be used for induction hazard studies. Now, our model was coarse, low spatial resolution, derived from a sparse network of GDS data with a slow sampling rate. But GA is currently involved in a far more detailed magneto-telluric survey, where long period MT data are going to be collected at almost 3,000 sites in a rolling survey across the continent with about a 50 kilometre grid size. And the image there shows the proposed in progress and completed sites in that AusLAMP survey. So once those data are available, a far more detailed conductivity model will follow, and will provide much more information on the geological structure, and will also advance induction hazard studies. So I think it would also be very useful to have some continuously recording electric field monitoring sites, possibly at the geomagnetic observatories, to provide a baseline source of electric field data for induction hazards. And we do hope to enhance our collaboration with the engineers and coordinate a joint geophysical engineering study in the future. So that's the end of my part of the presentation. So I think I'll pass over to Liejun to answer any questions or clarify anything. Thanks.
So the hazards map just to show the risk factor of the GRC in the different geology background. So like you go this area, usually the magnetic fields are increased in the in the conductive area, and electrical fields decrease in conductive area, and in the resistor area just opposite. So any infrastructure in the West Australia, this will be subject more intense the electrical induced electrical fields during the magnetic storm. So this is have an indication.
And are those values significant for the engineering then?
That's right. This value you can see compare the east side of Australia, the value increased about 2 times compared to the east side of Australia. So when in the West Australia, when you do in the engineer step, you have to take a consideration more about GIC compared to the east side.
Thanks, Liejun. So questions from the floor? The front here.
Just one question. I noticed you had maps of our man-made conductors that we've got strung around the country.
Yeah.
We've got pipelines and wires. There's another network which is very extensive and very good conductors, is railways. Do these, I mean, I can see the less hazard from currents in the rail lines, although they are used in signalling, but also does this distort your measured data at all?
No, I think the railway we are consider is more like how to improve the not the erosion problem for the railway. And for our measure the conductive structure, we more look at the deep part of the earth. The surface or the surface in structure will not affect our the measurements. Yeah. So, yeah.
Trevor, I think you had a question.
Yeah, possibly another ignorant question. So how easy or difficult is it to forecast space weather, and I guess is it possible to provide warnings to avoid things like the 1989 brownouts, for example?
Yeah, I think the next step, we want to incorporate this model into the engineering step, and at the moment we are talking in collaboration with the Bureau of Meteorology. There are what's called IPS, Atmospheric Prediction Service in Sydney, and we try to feed this the model. The model mainly produces what's called telluric response. With the telluric response plus magnetic fields all around Australia, we can predict the strength of the GIC. So we can put this information into their network parameter. They can calculate how strong the current will be flowing in their network just during the magnetic storm time. Yeah.
More questions? Yes, Gareth.
Yeah, I'm just curious, how sensitive would the various results that you get be to the time period of the measurements? So say if you've got like 9 months of data on that grid, if you just feed your model to like half of that or something, to what extent would the results vary?
So it means for the prediction? So,
Yeah, I guess so for, estimating those, the parameters and the layers of the Earth, and then for predictions and so on,
Yeah.
So how robust would they be to just what happened to be the length of the data that you have?
yeah, I think the example we show is the data is a field data collected in the Hamilton Dam. It has about 2 years usable data with a 4 years period deployment. Like Auslan program, we'll probably deploy about 3 months, and a short period. This will be how good the estimation of the telluric response. So that certainly will affect they'll predict the electrical fields. Yeah. So probably the much longer data is better. Yeah. So this also, you see that the example show that Andrew just talked about why we are predict the electrical fields, measure the electrical fields so well in the Hamilton Dam station, because we have a 2 years continuously data there.
Any more questions out there? Unfamiliar territory for us, and the MT data, of course, is something that GAs have been collecting now or driving this OSLAM program for its implications in relatively shallow crustal areas and the implications for mineral resource exploration, where some of the early data sets have shown great promise in identifying critical crustal structures. So a completely different application space for this sort of data. Just goes to show the breadth of what one can do with individual data sets. Yes.
On one of your deeper conductivity images, you showed a high conductivity zone which kind of almost goes north-south along the Western Australian border. Got any comment on that and what might be causing it?
Oh, yeah, okay. You talk about the one approximately across this way? Yeah, I think there was, this has just happened in the Canyon Basin and maybe the Office Basin, the conductivity. For the shadow structure, we probably correlate this conductivity with correlation between the craton, the Western Australia craton, to the northern and South Australia craton. So, and all the possibility cause for this conductor, always people have using was a possibility the graphite or sapphire or the magnetite or the partial melting during those geological processes. So this really depends on the geological process in this area. So yeah.
I think there are still real challenges in interpreting crustal conductivity data. There are generalised statements from people saying, oh yes, we understand it all. Well, I remain to be convinced, shall we say, that we do. So, much work to still do in tackling that issue. Well, if there are no further questions, perhaps you'll join me, first of all, in congratulating Andrew and Liejun both on their DGA and on a really excellent and informative lecture, uncovering, I think, a range of aspects that many of us are just not familiar with, but really significant implications of